Hope I am audible. So, today is the last tutorial session. Okay, I will conduct in this semester, and in these tutorials I will discuss a random walk, okay, using Monte Carlo simulations. Okay. So, let me share my screen first. Yeah, okay, hope my screen is visible. So, okay, so in this tutorials we discuss random walks using Mathematica. Okay, and a random walk. What is a random walk? So, random walk is stochastic and random process. Okay, which describe a path consisting of successive random steps. Okay, and we calculate the path. Okay, or to describe the path, we basically accumulate the steps. Okay, so basically we perform a sum over all the steps. Okay, to describe a path. Okay, we will discuss this in details in a minute. Okay. So, so let us first start with a random walk. Okay, so 1D random walk. Okay, so basically we move only in the one directions. Okay, so mainly we move, let us say, only on the x axis. Okay, both positive and negative. Okay, so but the dimensions is 1. Okay, so only one axis we move along that axis. Okay. So, Monte Carlo simulations use random numbers. Okay, and so how to generate random numbers? So, in the previous class we discussed that. So, let us say I generate a random number in between -1 to +1. Okay. So, you just call a random real, that is embedded in the Mathematica, okay, and put the limit. Okay, within that you want to generate a random number. So, I put -1 to 1. So, basically I want to generate a random number within -1 to 1. So, I just call random real and the range. Okay, so this is, you see that -0.73 is basically in between these. Okay, you can also do next times basically get a different number. Okay, so let us say I want to generate a 5 number. So, you just put comma 5. Okay, how many numbers you want, okay, within that range. Okay, and that is a random numbers. Okay. So, you just use this 5, or if you put 10 here, so you just get 10 numbers. Okay. So, now how to generate random choice? Okay. Let us say I define my move are basically, so I define a random walk where each step we move +1 or -1 with a equal probability, right. So, let us say you are starting at origin. Okay, so you can move in +1 in the positive, or you move -1 in the negative. Okay. So, you can move both have same probability and equal probability, right. So, both have a equal probability. So, you can move +1 or -1, okay, from the origins. +1 means the positive directions, -1 means the negative directions. Okay. So, and we choose only one, right, because we have only 2 options. Okay, +1 or -1, I choose only one. So, that is why you can randomly choose the -1 to +1. Okay. So, you just put random choice, okay, and the allowed values are the -1 or the +1. Okay. So, this is not a range. Okay. So, where is the values? Okay, the allowed values. So, I allowed the 2 values +1 or -1. So, you just put random choice within these 2 number. Okay. Okay. So, if you just call, so this is 1, next time -1, third times 1, fourth time -1, because of a equal probability, right. So, both have a probability half of getting, right. So, if you perform it, let us say coin. Okay, how many times you get a tail, or how many times you get a head. Okay. So, if you perform a large number of times, so you basically half. Okay. So, that is why. So, if you just so here I am not assigning any probability, that means they are equal probability. So, their probability are basically half. Okay. You can also generate, let us say I generate the 5 random choices -1 to 1. So, you can easily generate, right. So, 1 1 -1 -1 -1. Okay. So, you can generate in this way. Yeah, so you can generate randomly, okay, the steps. Okay. So, that is the random walk. Okay, we define it, and we can also assign the probability. Okay. So, here basically I choose -1 to -1 or +1, but with the probability of getting -1 is 0.8 and the probability of getting +2 0.2. I assign those probability, okay, to choose these numbers. Okay. So, answer to do this, you see that the minus 1s next times is again minus 1 because the minus 1s have probability 0.8. Okay. So, most of the times you get minus 1s, or only few times you get the plus 1s, okay, because the minus 1s have a high probability. Okay. So, you just let us say I want to generate 5 numbers for this 5 choices. Okay. So, you see that most of the times you get minus 1s. Okay. In this case 5 times you get a minus 1s. Okay. You once you do let us say 10 times, you see 3 times you get minus 1, then plus 1, again you get all the times, rest of the times are minus 1. Sorry. So, among this 10 choices, you see the one choice of the plus 1 and the 9th choice are minus 1. So, now we change it. Let us say I want to reverse this thing. So, here I assign the probability 0 p equals to 0.2 to getting minus 1, okay, and to get plus 1. What is the probability for that? I assign 0.8. Okay. So, now if you do, you see most of the times you get plus 1s, but the only one time you get minus 1s. Okay. You can do increase the number of times. Okay. See, you get 3 times minus 1s, but the remaining 12 times you get plus 1. Right. So, in this way you can manipulate the choices. Okay, just assigning the probability. Okay, that is not half. Okay. So, if you put 0.5 and 0.5, that is basically the same thing here. Okay. So, this is basically this. Okay. So, you see now you count, okay, how many times you get plus 1, how many times you get minus 1. Okay. Now, if you do this is large number of times, is basically half. So, half of the times you get plus 1, half of the times you get minus 1. Okay. So, this is very small number. So, you have to perform a very large number of experiments, okay, and then you will get half. Okay, that is the random theorems, okay, that tells you that if the probability is half. So, now how do I define the random walk? So, basically I define a simple random walk. So, is basically I choose minus 1 to 1, that is n number of times, okay, and so this is basically are the things, right. So, I choose minus 1 and 1 n number of times. Okay. Okay. So, that is I already discussed here, and now I add prepend. So, basically I add 0 to the list, okay, right, because I start from the origin. Okay. So, that is why I put 0, okay, and my first steps plus 1 or minus 1s, okay, and that actually choices that actually appear here. Okay. So, I basically enlarge the list by adding the origins. Okay. That is why I add 0, okay, to this list. Okay. Because I start from the origin, okay, and I then I basically accumulate. Okay. So, accumulate is basically cumulative sum. So, up to let us say I have 2 steps. So, I accumulate this sum of these 2 steps, and then after 3 steps I add again 3, okay, so and so on. So, at each steps I add all up to that stage I add all the paths, so all the steps to describe the path. Okay. So, that is by doing accumulate. So, that is done by calling these functions, okay, accumulate. Okay. So, this is my simple random walk, okay, and yeah. So, I already discussed that the prepend is basically I preparing the data, okay, that is start from the origin. Okay. If you put let us say plus 1, then basically you add extra plus 1 number to this list. Okay. So, that is prepend actually. Okay. So, now if you define this random walk, okay, now I plot random walk, let us say 500. Okay. So, basically 500 steps, okay, are there, and I want to plot. So, this is list line plot. So, basically you have to connect the dots, okay, and these are the labels and the plot style and these things. So, you will see. So, this is your path. Okay. So, first you generate a list, okay, consisting of plus 1 or minus 1s from this, okay, and then you add 0 to this list, okay, by calling this prepend, okay, and then you accumulate. Okay. So, in the last 2 or 3 classes I mean repeatedly discussed this, okay, accumulate functions. Okay. So, accumulate is basically sum of this steps. Okay. It is not the total sum, okay, it is the cumulative sum. Okay. So, you see you start from the origins and then first step, second step is sum of this thing, okay, and then repeatedly we summing over the steps, okay, and we get the path. Okay, so this is the path. If you do the second times, if you run again, it will lead to some different path. You see. So in the previous case, it is oscillating, okay, and in this case, it is basically growing. Okay. Okay, just a minute. Right. So average positions of the worker state at the origins, okay, both +1 -1 step have equal probability. So if you have after many steps, right. Right. So how do I check this? So because I have okay, I have only two move, right, two options, +1 or -1, so with equal probability, right. Just a minute. Okay, so right. So since we have two options, +1 or -1s, okay. So the average positions of the worker should be at origins, okay, because both +1 or -1 step have equal probability, right. So if we calculate after many steps, okay, so the average should be at origin, okay, right. And all the steps, since all the steps are independent, so the variance is n and the standard deviation is square root n. We will check this, okay. So here n is basically the number of steps, okay. So the mean 0, but the variance n, okay, and the standard deviation is basically square root of n, right. You can easily calculate because the mean is 0, right. So for this we generate, let us say 500 paths, okay. So this is basically we generate 50 paths, okay, simultaneously, okay, and each path we have 1000 steps, right. So that is basically random walk 1000, basically 1000 steps, okay. So that is for one path, okay. Now we generate large number of paths, okay, and then you calculate the average positions, okay, of the walker, okay, okay, and this is the one path. Now I generate similarly 50 paths, okay. So first I make a table for that, okay, for one and remaining 50 times, okay, and I plot these paths, okay. So if you do these things, okay, so you see, so this path, let us say I focus only this path. So one path goes up, another path goes down. So average, you see, you start from the origin. So this is your origin, okay. All the paths start from the origins because I define my random walks from 0 origins, okay, right. So all the paths start from the origins and then scatter, okay. But the average, you see, if you calculate the average at each steps, okay, you see stay at the origins, okay, over all the paths, okay. So this is for 50 paths. Now you generate large number of paths, let us say 500, 5000 paths, okay. You can easily generate, let us say I generate 500 paths, okay. So you see the average is still, I mean, 0, right. So once you calculate this from the pictures, you can easily see that the is basically spreading around the origin, okay, I mean around the x axis, okay. So this is your x equals to y equals to 0 line, okay. So around that, okay. So this is clearly mesh. So you just look into 50 paths and you can see, okay. So once you increase more and more paths, so this becomes clear, okay, why this is and if you also calculate the variance is basically n, okay, you can see, right. So once you increasing n, your deviations is large, right. So if you see, let us say So, this is your n equals to 1000, right. So, this one is n equals to 1000, this one is n equals to let us say 400, 200. Okay. So, you can see at 200 the spread is small, but at 400 spread is large, 800 is again too large, thousands even larger. Okay. So, as n increases, okay, your spread is increases, that means the variance is increases. Okay. Standard deviations is basically follow square root of n. We will see. Okay. Okay. So, let us say I have a 1000 steps and I calculate the final positions. Okay. Because this is the cumulative sum, let us say I calculate only the final positions in order to show you that how these final positions actually vary with square root of n. Okay. Once n increases, their final positions basically increases. Okay, is basically proportional to square root of n. Okay. So, I just only calculate the final position. So, final position is basically if we add all the numbers. Okay. So, basically I calculate here the total. Okay. So, basically the last one. Okay. So, accumulate is basically we are adding the numbers, okay, adding the steps, okay, one by one, but total is basically once you calculate, let us say I want to calculate the final positions, that means I have to add up to those points. Okay. So, that is basically total. Okay. So, I define n steps. So, I calculate the total of this list, okay, and I do for the 50 times, okay, for 50 different paths. Okay. So, I calculate basically the final positions for 50 different paths. Okay. You can also calculate extract, okay, the last one from this path. Okay. So, if you just put the last numbers, okay, in the list, okay, that is actually also works. Okay. So, instead of using total, you use accumulate, but you extract the last one in the list. Okay. Because accumulate is also gives you a list, okay, but the total is gives you a number, so only one number. Okay. So, so this is the final positions I calculate for 50 different path, okay, and each path have 1000 steps, okay, and then you calculate the mean and you calculate the standard deviations. Okay. You see that the mean is basically 0.84 and the standard deviation is basically 33.7. It's large, but mean is basically around close to 0. Okay. Right, you can see, right. So, mean is basically around 0, but the standard deviation is large, right. Now, I exactly see how we want to see how the spread actually grow with time, okay, or basically the steps. Okay. So, yeah, so basically now I basically calculate the RMS one, right. So, how to calculate the RMS? So, it is basically root mean square, right. So, I first calculate the things, okay, and I extract. So, this is an accumulate, right. So, I extract. So, this is the take, okay. So, I use. So, I extract the only after, let us say t equals to 10. So, after 10 step I extract the number, and in gap of 10 up to 100. Okay. So, it is basically t 10 to n steps. So, n steps your 1000, right. Yeah, n step your thousands in gap of 10, right. So, that means t equals to basically 10, 20, 30 up to 100. Okay. And I calculate, I extract the final positions at those times, okay, right, and then I calculate mean of this, okay, right. So, mean of this, and then I calculate the square root. So, in order to calculate RMS, so you first calculate this root mean square, right. So, first we calculate square and then mean and then square root, okay, and we make a table, okay, for that, because we have a different time. Okay. Okay. Now, I plot this, okay, and you see. So, as time goes on, your fluctuations is large, but you also basically away from RMS displacement is also large. Okay. Right. So, if you just compare with square root of t, so this is your RMS and I plot the square root of t again with the same steps and okay. So, I plot square root of t and you see, but there is a large error, right, large deviation. So, you have to so this is an RMS for one path, right, but it won't consistently show the square root of t scaling behavior, because the single worker might just happen to stay near the origins, right. So, you have to do I mean you have to average over many paths. Okay. So, you need to average over many different workers. Okay. And then calculate the RMS of all their positions at each time stamp t. Okay. So, basically at every time stamp t you calculate the RMS of all I mean of many different workers. Okay. And each worker have different paths, right. So far I just calculate for one path, okay, I mean one worker. So, one workers I calculate this. Okay. Now, we have to do for many workers. Okay. Okay. So, right. So this is that. So, basically I first define n step. Let us say my step are 500 and number of workers basically 1000. Okay. And I create a n sample. So, this is basically my sample. Okay. So, this is random walk steps. Okay. So, that is the path, and how many times? 1000 times. So, that means each row have a one path. Okay. Basically one worker. Okay. Different row, different path, different worker. Okay. So, you have 1000 worker, number of workers are 1000. Okay. So, you have 1000 different paths. Okay. Right. So, this is my n symbol. Okay. Now, if you transpose this, so this is your time slices, right, because once you transpose, your row becomes column, right, and the columns are basically now the time stamps. Okay, and this is basically your now row. Okay. So, in this case, in this ensemble, okay, so each row have a different path. Okay, and the columns are basically time stamp. Let us say 10, 20, 30, 40 up to 100. Okay. So, it is a gap of 10. Okay. Once you transpose this, okay, so you get a time slices. Okay. So, then becomes time slices at the rows, right. So, each row tells you that one particular time, okay, what is the positions of the workers. Okay. So, that is the columns. Okay. Okay. So, the average is basically you calculate the mean at this time slice. So, let us say at t equals to 10 I calculate the mean. So, that means, so this is basically map to. So, I calculate mean at this time slices, let us say 10. So, at t equals to 10 I calculate all the paths, okay, at the mean of all the paths, okay, basically at that time. Okay. So, at that time you know the positions of the paths. Okay. Here, right. So, each columns have a positions of the different paths, okay, and you calculate the mean. Okay. This is your average at a given time slice, and then you calculate RMS, okay, at a given time slice. Okay. So, these two things are basically calculate the average and RMS over 1000 path, okay, at a given time slice. Okay. And we do same thing for a let us say 10 to 100 with a gap of 10, okay, and we plot with the square root of t, okay, average and RMS, okay, right. So, I visualize those things. So, once you do that, I think there is okay. So n steps are basically 500. Why is not sorry? So this is small s and yeah, yeah. So now we see. So your average positions is almost 0, right? For each path, when you for each time slash, okay, when you average over all the paths, it's 0, right? As expected, right? So if you just see here, right? So at each time slice, okay, you calculate the average over all the paths, you get a 0, right? Because this is actually spread around the basically y equals to 0 line, that is around the x axis, okay. So at every timestamp you calculate, you get average is basically very close to 0, okay, almost 0. Okay. So if you do a very large number of paths, if you increase more and more paths, okay, you are getting closer to 0. Okay. So this is actually happens. Okay. So here I use 10,000 path. Okay. So at each timestamp you see it's very close to 0. Okay, it's almost 0. The average one, average positions. Okay. Okay. Whatever your time slash is. Okay. But the RMS displacements is the blue one is basically increasing. Okay. Once you increase your time. Okay. Right. And if you just so your this is the black one is basically square root of t. You see the exactly follow. I mean very close to square root of t, and exactly follow the trend. Okay, so that is very important. Okay, in case of random walks, that how it's scaling. Okay, and how do you observe. Okay, so this very simple examples. Okay, we actually got this trend. Okay. Square root of trend, okay, the RMS displacement. You can also check. So let's say at 500, okay. So what is the values of square root of t? So it's 12.36. Sorry, 22.36. So you see, this is your 20, 22. This is your 20, 21, 22. It's 22.36. This is your 22, and then this one is 22 and n equals to 500. So just above 22. Okay. So actually this square root of a at t equals to 500. You can also manipulate. Okay, so manipulate is basically I put a n list. Okay, sorry, n step as a variables, and I calculate this path. You see, if you just only 10 step. Okay, you see this is zigzag. Also increase the number. Okay, so this is for one path. Okay, you see how this is actually changes. Remember, this is only one path. Okay, you have to do once you calculate the average or RMS at a given time stamps. Okay, and you have to get these results. Okay, so you have to do over many paths, okay, at a given time stamp. So this is the things, and yeah, you can also plot the histogram. Okay, so yes, so here, okay, what is the histogram here? So basically, I first I choose -1 to 1. Okay, n times, and right. So this is basically two numbers, -1 or +1s. I can make a list. Okay, and then I accumulate, and then I extract the last one, the last positions. So basically, you can also, so the so in the previously I calculate using this total. Okay, but you can also do this way. So first we calculate accumulate. Okay, and then we just extract the last ones. Okay. That is actually up to that point you calculate the total. Okay, because accumulate is basically summing the things. Okay, the rest of previous ones, all the previous ones. Okay. So that's why the last part actually gives you the number that is basically add to the all the numbers in the previous in the list. Okay. And we create a table for 5000 times. Okay. And where n are basically varies from minus n to n with a gap of 2. Okay. And we perform for different n. Okay. So, that is I performing manipulations here. So, you will see here. So, this is for n equals to 10, right. Now, what do you expect? Okay. So, if n increases. So, you see that for n equals to 10, you are basically around the origin. Okay. So, your mean 0 and this is looks like a Gaussian. Okay. And your standard deviation is basically follow square root of n. Your standard deviation is 10, square root of n is 10, right, because you choose n equals to 100. Okay. Right. Okay, that is I calculate theoretically, just you calculate square root of n, because I choose n equals to 100. Okay. So, this is n equals to 100 and you can also see here. So, this is 100 okay, steps and you calculate square root of n is 10. Okay, that is the theoretical value, and you can see here the standard deviation is also around 10 okay, sigma, and your mean is always 0. Okay. Right, because I actually calculate the same way as I did here. So, yeah, I calculate the total, basically I extracting the last ones and make a histogram for that. Okay. So, this is the plot range and table. Now, what do we expect if we increase n? So, first of all, this histogram is clear or not, right. So, I have a 5000 path, okay, and I make a histogram for this, okay, for each n, right. Similarly, as I did here, right. So, for each step, so here my the timestamp. Okay. So, for each step time slices, I calculate 1000 path and their positions, okay, and RMS values, right, average values and then RMS values, right, and we get this. Okay. Average values is 0 and the square root of n. Now, I see in terms of histograms. Okay. So, in the language of histograms, basically I calculate the last final positions, okay, for 5000 paths, okay, and my n are basically varies from 10 to 1000 with a gap of 10. Here I am showing the result for n equals to 100, and the bin size are basically minus n to n with a gap of 2. Okay. So, if we choose let us say n equals to 100, so your minus 100 to plus 100 with a gap of 2, okay, that is my bin size. Okay. So, each bin how many numbers are there, right, among this 5000. So, you see most of the things are around 0, okay, right. This is your average, and the deviations, okay, at the half maximum is basically your standard deviations. Okay. So, you can calculate the 68%. Okay, if you fit to a Gaussian's curve, and then you calculate the 1 sigma. Okay. Yeah, so 1 sigma is not at half maximum, the width at half maximum, but that is different. So but you have calculated 1 sigma of this. Yeah. So, now what do you expect if we increase n? So, if you increase n, your average still at 0, right, but the standard deviations of the RMS displacement increases, right. So, your sigma is actually grow with square root of t, right. or square root of n, right. So, standard deviation is increases, right, at square root of n, okay. And you also see here, right, square root of t, as time goes on your basically spread is actually increases, right. So, now you can also see here. So, if you just increase, let us say 10 to 190, you see spreading, right. So, now if you increase more and more and more, yeah. So, average still at 0, but the distribution is basically spreading, okay, over n, okay, because square root of n increases, right, the number is here, right. So, you see, right. Okay. Right. So, it has become clear, right, that how the distribution is actually spread over time, okay, or over n. So, quadruple the number of steps. So, if you increase the number of steps 4 times, your width of the distributions only doubles, square root of n 2 times, okay. Right, because this is square root of n. How does the work behave as n goes to infinity, right. So, so then we have basically increase the number of paths, okay. So, let us say I have a 10,000 paths, okay, and I plot a histogram for that for 10,000 path, okay, and I normalize to this PDF. So, I use PDF here for normalization. Okay. So, this is a probability density function, okay, such that the total area under the bars, and if we add those numbers, basically sum is 1, okay. And I only so draw a histogram for these endpoints, okay. So, once you do that, you see. So, this is looks like a Gaussians, okay, as n goes to infinity, okay, is actually a Gaussian. So, if you fit to this, okay. So, I have a Gaussian curve with let us say 1000. So, I calculate the mean 0 and what is the standard deviation, the square root of, I have a n, right. So, 1000 path, right. So, 10,000 steps, okay. So, my n is 1000 and this is 10,000 path, okay, right. So, my standard deviation is square root of n. So, I calculate square root of n here, okay. And so I basically plot a PDF. So, probability density functions for these distributions, okay, normal distributions, Gaussian distributions, okay, and my range are basically minimum of the endpoints to maximum. So, if you see that, right. So, this is a pure Gaussian, okay. From this and the histograms are basically this, okay. So, I show hist and Gaussian curve in one plot, okay, and the blue one is the Gaussian's fit, okay, that I calculate theoretically, that what is the square root of n and 0, and so it is not fit, but it is basically Gaussians with these numbers 0 and this mean 0 and standard deviation is this, and your histograms are basically drawn from this from this random walk, okay. This is very close match. Okay, so this is the thing. So, this is basically known as the central limit theorem. So, once you increase n more and more, so it basically converts to a Gaussian's with to a Gaussian's distribution. So, that is the central limit theorems. So, up to this point is clear. Right? So, remember the 10,000s are basically 10,000 different paths, and the 1000 is basically the steps. Each paths have 1000 steps and 10,000s is basically different path. Okay. So, here when I saying that this how does the works behave as n goes to infinity. So, this is basically the number of paths. Okay. So, let us say let us denote this to be capital N. Okay, so this is basically okay. So, it's basically capital N goes to infinity. So, let it goes to N goes to infinity. So, this is the number of paths. Basically, averaging over more and more paths at each time step, and that is actually follow the Gaussian. And this is the central limit theorem, because your n symbol is large. So, you have to perform a large number of experiments. So, now we adding a drift, okay, or bias, and this represents an external force. For example, let us say an electric field acting on a charged particle. So, if we add a bias to the systems, right. So, initially I choose a random process where I am getting plus 1 minus 1 both have equal probability, half half, right. Okay. The probability of getting plus 1 is half, probability of getting minus 1 is half. Okay. And for this case we see that the mean is 0 and the standard deviation is basically square root of n, okay, for this process. Now, if you add bias, okay, so your p is the probability of moving plus 1 is the p, and probability of moving minus 1 is basically q, that is 1 minus p, because total have a 1, right, because I have only two possibilities, plus 1 and minus 1s, right. So, if p is the probability of moving plus 1, then 1 minus p is the probability of moving minus 1. So, this is the bias, and how do I add this bias in my system, right. I basically use this random choice. So, initially I calculate yeah. So, when you draw a number from plus 1 minus 1 with the probability of half, so basically you can put this way, okay. So, the probability of getting minus 1 is first one 0.5 and probability of getting plus 1 is again 0.5. And for bias works, okay, you have probability, let us say p probability for getting minus 1s, and the probability of getting plus 1s is p, okay. So, this is the probability, okay. And yeah, and the probability of getting minus 1s, okay, is 1 minus probability, okay, right. And the probability are basically the variables, okay. So, that go from 0.1 to 0.9 with a step of 0.05, okay, and I manipulate the things, okay. So, the first one is the generate fair work, okay. So, it is basically half of probability, okay, probability of getting plus 1 or moving plus 1s half, probability of moving minus 1s is minus 1, sorry, half, okay. And for bias works, I do not know what is the probability. So, I put a list here for this probability range. So, range is basically 0.1 to 0.9 with a gap of 0.05, and I basically create a slider for that, okay. And then I basically accumulate all these paths and I plot, okay. Just I did before, okay. So, the two plots, one for the fair path, another for the bias path, okay. Okay, and yeah, and I also plot the mean, okay. So, the average one, right. So, you calculate the fair average for the fair path, you calculate the mean of fair path, okay, and you calculate the bias average, the mean of bias path. Okay. That every time stamp you, so this is your bias path is basically know the list of the final positions of the path for each path, and we have how many paths. So, n walk. Okay. So, n walk is basically 50 and n step is 200, right. So, I have a 200 step and 50 paths. So, and I calculate at each time stamp, okay, I calculate the average of this path, okay, that is my for the fair path the fair average, and the bias average for the bias path. Okay. And I also plot this, okay, for the fair path I plot the fair average, okay, and for bias path I also plot the biased average. Okay. So, thread is basically combined element by element. Okay. So, you see that this is basically your range and the fair path. Okay. So, this range are basically 0 to n steps, okay, with a gap of 1. Okay. So, 0 1. So, how many steps are there? 200, and each steps I calculate the fair average. So, I just plotted x versus y. Okay. So, this thread actually basically make a table, okay, 1 by 1, okay, and then I just plot line plot for that. So, and so do this. So, this is the for 0.6. Okay. So, you see for okay. So, the probability only applicable for the p 0.6 for the bias path. Okay. For the fair path is 0.5. Okay. Because this is the half a probability. Okay. Okay. So, this probability is only applicable for the bias path, okay, because you see I use this variable for the bias path. So, you see for 0.6, if the probability is 0.6, okay, for moving plus ones, you see the trend is positive, okay, it is not 0. For the fair path is basically around 0, okay. Your average around 0 and spread basically again square root of n, but here also spread around the average things, you see is increases, but the average is shifted, okay, as time goes on. Okay. Now, if we increase let us say 0.8, right, you see that the spread even decreases. Sorry, spread is irrespective to the origins is increases, right, as the time goes on, but your average is also increases. You see, right. So, the fair path still remains at the origins, okay, but the bias is changes, so once you change the probability. So, how this thread works? So, is basically so this is the new things that that we learned today. Okay. So, thread is basically, let us say I have a list x 0 1 2 3 4 5 and y I have another list 0 0.1 0.3 this, and the thread is basically we make a table, okay, and that is 1 by 1. So, I have create x 1 y 1 x 2 y 2. So, this is basically a array where you see. So, this is 0 0 1 0.1 okay, and 2 0.3. Okay. So, this is basically a n cross 2 matrix, okay, if there is n elements. So, this gives a n cross 2 matrix. Okay, all right. So, now we using this, we plot the average distance over all the path, okay, at a given time stamps. Okay. So, that is the red lines that we actually did here, and we know the range is basically 0 to 5. So, here I use this. So, 0 to n steps. So, if we do not put any number after that, okay, it is basically by default we set 1. Okay. So, that means it create x coordinate uniformly from 0 to 5 with a gap of 1. Okay. So 0, 1, 2, 3, 4, 5. If you put let us say 0.3 here, so that means they create a list, okay, from 0 to 1.5 with a gap of 0.3. Okay, you see. Okay. Yeah, so far any questions? Okay, so if not, then will discuss few problems. Okay, that is, related to your assignment problems. So the first problem is that let us say a random walker walking along the x-axis, okay, has a slight bias to move towards the right. Okay. So that means this is a bias problem, okay, that I already discussed here. Okay. For the probability, it's basically various probabilities. I make a slider here, okay, for the probability, bias probability. Okay, we can also cross check here. Let's say I put p equals to 0.5. So if you put p equals to 0.5 here, you see the average goes down to 0. Okay. Now go to the negative. P is small, okay, then your average distance are negative. Okay, because the moving -1 is large probability. Okay. And the moving +1 is the small probability, 0.35, okay, less than half. If you give me more and more, it's basically opposite trend. Okay. If you have a p 0.8, that means the probability is basically moving +1. Okay, probability this p is basically for moving +1. So, okay, if it is more than your -1, so it basically overall positions in the positive directions. Okay. But if the probability less than half, then the overall positions is the negative directions. Right? So the average positions is the negative direction. That's why you do opposite trend, okay, in the negative directions. And the speed is still increasing. Once you increase the n, okay, that you can see. Okay, so so here we also consider a bias problem, okay, and each point we move to the right. So that means the +1 with a probability p 0.65. So if he start at the origin, okay, and takes 100 steps, what is the probability of finding him at x equals to 50? Okay. So you see here, the probability is basically greater than half, right? So that means at x equals to 50 is the positive, right? Right, along the x axis. So, it is a 1D random walk, okay, along the x axis, that means x equals to positives. Okay. So, that means there is a probability. Okay. To getting in the positive direction. So, because my probability is basically moving to the right is large. So, that makes sense. Okay. So, let us calculate this. So, okay, here I introduce two parameter. One is the NR. So, this is basically the number of steps to the right is the +1, moving +1, and NL is the number of steps in the left, okay, -1. Okay. So, how many steps? So, total step in is basically 100. Okay. So, that is basically NR plus NL. I do not know, okay, how many steps are on the right or how many steps on the left, but the total is 100. Okay. The total steps here. So, this is 100 steps, and my net displacement, okay. So, net displacement is basically x equals to 50, that means in the positive direction, right. So, that is why my NR minus NL. So, NR is basically the number of steps to the right. So, since the net displacement in the positive directions, okay. So, the NR is large, right. The number of step on the right is large than the number of left, okay. And also this is from also expect from is the probability is large, okay, okay, for moving plus 1. Okay, probability of moving plus 1. Okay, so then so your net displacement is basically NR minus NR is 50. Okay. So, basically you have to calculate NR, okay, from these two equations, okay, given the probability is P 0.65. So, how to calculate? So, this follow binomial distributions, right. So, calculate from the binomial distribution. So, I have a 100 step, okay, and I have only two possibilities, P and 1 minus P. So, P is 0.65, 1 minus P I calculate from this. So, it is basically 0.35, okay, and my NR is 75, because you just solve here from these two equations you calculate NR and NL. So, yes, so you put NR here. So, this is the result. So, what is the probability? Then 0.009, right. So, they follow the binomial distribution. So, your binomial is basically yeah. So, total steps is 100 and your NR is 75, okay, because this is so the number of steps on the right in the plus ones, okay, because your net displacement in the positive direction. So, and use P to the power NRs, okay, because the probability of moving plus ones is 0.65. So, that is why P to the power NR and 1 minus P to the power N step minus NR. Okay, so this is the answer. Now, we can change the probability, can easily calculate from this. You can easily calculate, let us say change this to 60, right. So, you can easily calculate for this. So, you just solve these two equations, this one and this one, and calculate NR and NL. Okay. Once you calculate this, so you just put it here. So, you just put there and you got the result. So, it is not a difficult things. Okay. Okay. So, now I am going to discuss problem 2. So, in problem 2 we calculate the ratio of Stirling approximation, okay, to the exact factorials. Okay. So, what is the Stirling approximation? Stirling approximation is basically n factorials, okay, equals to square root of 2 pi n times n over e. So, this is basically log e. Okay. So, it is basically the power of sorry the subscript of log. Okay. So, ln is log e. So, this e here. So, n over e to the power n, okay, and I calculate the ratio. Okay. And so, we know that this Stirling approximation is valid for large n. Okay. We will see here. Okay. So, by calculating the ratio. Okay. So, calculate the ratio, let us say for n equals to 10. Okay. And then determine the minimum integer n required for these ratios to be 0.1% of unity. Okay. Either ratio must be greater than 0.999. Okay. It's 0.1%, right. So, the last digits will be 9. Okay. Okay. So, let us do that. Okay. So, first I calculate this ratio for n equals to 10. So, let us say n equals to 10 and the Stirling one is basically square root of 2 pi n over e. So, it is basically exponential 1. So, that gives you this e and to the power n, and the actual value is basically 10 factorial. So, and then you calculate the ratio, okay, up to 20 decimal place. Okay. So, you see 0.9917, right. So, that is not within this. Okay. Okay, that not satisfy these conditions. It is not greater than 0.999, it is basically less than 1. That means, you increase n. Okay. So, n is 10 is not good for these approximations, okay, within this accuracy, within this accuracy. Okay. So, let us do for various values of n. Okay. Okay, any question? Okay. So, let us do this for various values of n. Okay. So, here I create a again a manipulate things, okay, and I vary n from 1 to 100. Okay. So, first I calculate the exact one, that is n factorials, and the approximations is basically stealing approximations, square root of 2 pi n and n over e. So, this is also is basically exponential 1. So, you can also write e here. So, this is your stealing approximations, and we calculate the error from the difference between the exact minus approximations over exact times 100. So, this is the error, and we calculate the ratio. Okay. These approximations over exact. Okay. Okay. And yeah, here I create a column. Okay. So, in the first I put the exact number, okay, for a given n. So, okay, so in the first column I put n, and the second one the exact factorial, and the third column the stealing approximations, okay, that is the approximations, and then I calculate the ratio in the fourth column. Okay. Okay. So, I calculate the ratio, and yes. So, this is the grid, I make a grid. So, basically I make a table here for this, and I put some space, and then I plot. Okay. So, basically I plot here the square root of 2 pi x over e x over gamma x plus 1. So, here I am not using factorial. So, gamma x plus 1 is basically x factorial. Okay. So, I use a functions here. Okay. So, gamma functions. Okay. So, gamma x plus 1, and my x is vary 1 to 100. Okay, I plot this, and the n is also changes. Okay. So, now if you see, yeah, I also put a epilogue here on these plots, okay, for the n. So, that gives you. So, let us say for n equals to 10, I first calculate these numbers. Okay. So, these tables. Okay. For n equals to 10, I calculate the exact one, approximations one, and the error and the ratio, right, and I print those numbers, ratio, approximations, exact, and n, right, and then I plot this. Okay. So, this plot is for all x, okay, 1 to 100, but in this plot, okay, I put a epilogue. Okay. So, basically add extra item, okay, or extra graphics to this plots, that is rate points. So, I basically add a point, okay, where the number is actually on this plot, okay, for n equals to 10, because I choose n equals to 10 here. So, defined n I just put. So, basically that indicate that where your number is on that plot. Okay. Okay, just a minute. Yeah, I think my screen is visible. So, if you do this Stirling approximations and make a plot of this ratio, okay, so you see, so for n equals to 10, your exact factorials is basically 3.6288 times 10 to the power 6, but the Stirling approximations gives you 3.5987. So, your ratio is 0.9917, okay, that we calculated before. Okay, and you see from the plot, okay, so this is basically from n equals to 0 to 100, okay, and this is for n equals to 10, okay, the red dot, okay, you see the red dot, okay. This is for n equals to 10, your 0.9917. Now, if you increase n, so closer to 1, okay. So, you see 0.999 is basically at around n equals to 90. Okay, so once you reach n equals to 90, the ratio is again, yeah, so this is 0.99. Yes, so around n equals to 82, you get 0.999. Okay, the ratio. And from this plot, see that for n equals to 1 and 2, okay, this approximation is not good, okay, because the ratio is very small, okay, that means the deviate from the actual value is large, okay, the deviations from the actual value is large, okay, the exact value. So, increase in, okay, so see here, your ratio is 0.92, that is very differ, okay, from 1, and once you increase into 1 to 2, it rapidly increases, but still not in the accuracy. So, let us say my accuracy is 0.1%, okay, within the exact value. So, I need n equals to at least 80, okay, above 80, okay, around 78, 79, 80. So, at n equals to 80, you reach this average. Okay. And another point is note that the green line is stay always below 1. Okay. So, that means the Stirling approximations is always slightly underestimates the factorial, okay, not overestimates this. Okay. So, always below your 1. So, your actual value is exact value is n factorial, okay, and the Stirling approximations gives you this this formula, this square root of 2 pi n and n over e to the power n. So, that you always underestimates this, okay, because the ratio is always less than 1. Okay. So, this is the thing. So, now I move to the third problem. Okay. So, for an so this is a problem 3. So, for an unbiased random walk, okay, so the mean square displacement scale linearly with the number of steps, okay, so that is basically m square average is proportional to n, where capital N is the number of steps, okay, and RMS is basically square root of n, right. So, this is a mean square average, and if you calculate the RMS is basically square root of mean square, right. Okay. So, then your RMS is basically proportional to square root of n, right. So, now we investigate the scaling behavior of the fourth moment. Okay. So, m to the power 4, okay, how m to the power 4 the fourth m to the power 4 and then average, okay, how it behaves. Okay. So, this is your fourth moment. Okay. So, this point is clear, right. So, let us again create a steps from 100 to 1000 with a gap of 100. So, basically 10 steps, okay, with 10 time slices, and the number of workers are basically 5000. So, number of workers are 5000. So, it is a large ensemble. Okay. And we calculate m to the power 4. Okay. How to calculate? So, we first calculate the n points, okay, from these random choices, okay, and then accumulate and then extract the last point. Okay. So, that is the end point, okay, for each of the workers, okay, and then I calculate end points, the mean of this, okay, where n goes through the steps. Okay. So, basically 100 to 1000 with a gap of 100. Okay. So, this is basically a list. Okay. For these values of n from this list, okay, I calculate this mean. Okay. Right. So, the table is basically I have a n the time slices, okay, and the calculate the mean at this time slices, okay, sorry, mean of m to the power 4, and this is my m to the power 4 data. Okay. I make a table for that. Okay. And then I perform a nonlinear fit to this data in this format, okay, ax to the power b. Okay. So, this is my model power law fit, okay, where a b are the parameter, okay, and x is the variable. Okay. That is nonlinear fit, okay, I use it. And I extract what is the values of b here. So, my results are basically b at this model, okay, and this gives you my best fit parameters. Okay. So, I extract the best fit parameters from this fit, okay, and I plot here. Okay. So, I plot in the log plot, okay, where I plot m4 data, say m to the power 4, okay, average over m to the power 4 I plot, okay, and then I plot the fit data, okay, and then I extract what is the values of b, okay, from this fit, nonlinear fit, okay, because this fit is basically power law fit. Okay. So, once you do all these things, you see your m to the power 4 actually goes with number of steps is basically this, okay, and if you perform a fit, your b is basically close to 1.95. Okay. So, it is basically you do more and more times. So, it is basically around 2. Okay. So, that means so this basically m to the power 4, the average over m to the power 4 is basically proportional to n square, right, because you see the x to the power b and b is basically around 2. Okay. So, that means your m to the power average over m to the power 4 is proportional to n square, okay, roughly. So, we can also generate an ensemble for unbiased random walks, okay, for this range of steps, okay, and for each n we can calculate the ratio. Okay. So, unbiased, I am not putting any bias. Okay. So, getting or moving plus 1 or moving minus 1s both have the same probability plus up. Okay. So, this is a unbiased random walks and I calculate the ratio. Okay. So, what should be the ratio for each n? Okay. So, by the way, this is clear, right. So, how this scaling actually. So, how the average over m to the power 4 scale with the number of steps, it's basically n square, right. So, you just see. So, it is around 2. Okay. So, now I calculate the ratio. So, using Mathematica I plot this kappa against n, okay, and what is the value does this the ratio approaches as n becomes large. Okay. And what does this tell us about the shape of the random walk distribution? Okay. So, I create a list for this range of steps 50, 100, 200 and 500 to 1000. Okay. And my number of walkers are basically 10,000, okay, large ensemble I choose again, and I calculate the ratio. So, first I calculate the n points. Okay. So, that is basically the last number in the list. Okay. So, last point last number in the list. Okay. So, that is my n points, and I calculate the mean of these endpoints for different paths. So, I have a 10,000 paths, okay, and means the 10,000 ensembles, and I calculate M2 for the from these paths, okay, which is basically mean, okay, and M4 is basically mean of endpoints to the power 4. So, M2 is the mean of endpoints square, okay, and M4 is basically mean of n to the power 4. Okay, and for this n list, so n belongs to this n list, n equals to 50, I calculate this, n equals to 100, I calculate this, and I make a table for that, okay, for each n, okay. And I plot this, okay, plot this ratio as a function of n, okay. So, how many points are there? 3 and 5. Okay. So, let us see how it changes. So, you see, so at n equals to small, your ratio is below 3 and actually it is gradually converging to 3. Okay. So, that means the ratio is basically 3. Okay. So, this ratio is converges to 3. So, this is the definitions of, okay, kurtosis of a normal distribution. So, this is the definitions of a kurtosis of a normal distribution. So, if we calculate the fourth moment, so that is basically x to the power 4 and then average. So, it is basically 3 sigma to the power 4, and if you calculate the second moment x square and then average, so you calculate the sigma square. Okay. So, if you divide it by this, your kappa is basically 3, okay. That is from the Gaussian distributions. Right. Now, you see that as n increases, the central limit theorems actually ensure that the discrete binomial distributions of the random walk transform into a Gaussian distributions. Right. So, each steps each paths follow a binomial distributions, okay, but over a large number of binomial distributions actually Gaussian distributions. Okay. So, this transform into a Gaussian distributions, and that is actually central limit theorem. And if you calculate the this ratio kappa for the Gaussian distribution, which is basically 3, and you see as n increases your from the random walk problems, okay, so you get also 3, okay, this converges to a 3. So, next we calculate this kurtosis of a bias walk. Okay. So, basically, so initially I assume that I have a both plus both have a probability plus up, but now I move to a bias problem, okay, and then I calculate the same thing. Okay. The kappa is basically square root the average, the ratio of m to the power 4 average and then m square average square, right. And let us see if this is converges to 3 or not. Okay. So, we basically use introduce a strong bias. This actually helps us to understand that how the symmetry of a distributions or is there any lack of symmetries in that affect the higher order moments. Okay. So, if you calculate m to the power 4 things and then m square and then calculate the ratio, this actually tells you that is there any symmetry or not. That means biased or unbiased. So, if you just calculate this, so I have again in list 100, 200, 500 and 1000, and my number of workers are basically 10,000, and I put a strong bias here. So, p is 0.8, and I again calculate this. Okay. So, m square m to the power 4 and make a table for that for all this n list. Okay. So, I calculate this and then I plot this. Okay. So, you see that this plot actually gradually decreasing to 1. Okay. So, it is roughly converges to 1 rather than 3. Right. So, this is because that in bias work the displacement is dominated by the drift. Okay. So, it is basically shifted to only one direction, sorry, because there is a drift that is basically v, okay, times m, the number of steps. So, to get the value 3, okay, because if we just calculate around the average, then it is fine, right, but the average is shifted. Okay. The average is no longer at 0. So, you basically calculate the moments, the central moments. Okay. Okay. So, how to calculate the central moments? You calculate the central moments basically m minus m to the power 4 m average. So, basically you subtract the average part from this. So, initially you calculate just m, the end points, and then calculate the square of this, but you always subtract the average. So, if you so you just look into this plot in the bias plot. So, if you calculate the distributions around the average red line, then you actually get a correct result, right. Otherwise, if you calculate the average around the origin or around the y equals to 0 line, it is basically biased, right. It is shifted in one direction, it is always shifted in one direction, depending on the bias in the positive directions or the negative directions, right. But if you calculate the moment around this axis, around the average, the red one, so that is your average one, right. So, we calculate the moment around these, so that is basically central moments. So, if you calculate, so basically subtract the m average from the m, and then you calculate this, that is the central moment. So, let us do this. So, here I calculate. So, the central moment is basically also defined in the Mathematica. So, you just call the central moment, that basically actually subtract the part from the end points, and then calculate this basically m square, and then Cm4, and then you calculate the ratio for the central moment, and then you plot. So, you see that actually converges to n, I mean very close to m, very close to 3. So, you have to increase more and more, but you see that. So, this actually very close to 3 as n increases. So, central moment only measure the spread, right. So, if you see here, right, once you calculate the central moment around the average, so that actually measure the spread, the central moment measure the spread. So, that is the crucial. So, let us given a probability density functions PDF for a single steps. So, now we basically do another problem. So, where they do not follow a binomial distributions, but they follow exponential distributions, and we see how it is goes to a Gaussian distributions if we increase m. So, let us first start with this, that we have a probability density functions for a single steps is basically follow this is 2 e to the power minus 2x, where x is greater than 0. So, basically I restricted only in the positive directions, right. And this is a standard exponential distributions with a rate parameter lambda equals to 2, and I calculate the spread is basically the standard deviations, this is basically x square average minus x average square, and the this is basically square root of the variance of x, that is my spread, the standard deviations. So, this is a exponential distributions, right, and that is defined only on the positive directions, because x is greater than 0. So, in this case the mean is not 0, the x average is not 0. So, you calculate. So, this is your total number of steps, and this is lambda, and my distributions is basically exponential distributions, and how many workers are there? 10,000. And I generate 10,000 numbers from these distributions. So, I generate this and I calculate the total. That is my the endpoints. So, that is the samples, and I calculate the numerical spread for this samples. So, I calculate the standard deviations. So, this is basically gives you the numerical numbers. So, this is double slope, this is not a divider. So, this is not a divider. So, that actually gives a numerical number for this, and this is a theoretical spread, this is square root of n over lambda. So, for these exponential distributions, your standard deviations is basically the theoretical values is square root of n over lambda. So, in this case lambda is 2. So, this is basically square root of n over 2. and we print these two values, and this the numerical spread, okay, that is calculated from this sample, okay, and we and this is the theoretical spread, okay, square root of n over 2. Okay. And we also draw a histogram for this, okay, and we will see that the average is in this case is not 0, but is shifted to the positive, because the distributions are defined on the positive line axis. Okay. So, you will see the average is basically 500, okay, around, because total we have a 1000 steps, okay, n equals to 1000. So, your average is almost n over 2, okay. And the spread is basically numerical spread is 15.79. So, this is calculated from this, okay, and the theoretical value is 15.8, is very close to that number. So, it is 7, 9 and 8. So, now if you also match with a histograms, okay, so what is your spread? The standard deviation is basically square root of n over 2, and the mean is basically n over 2, right. So, I draw a Gaussian distributions, okay, n over 2 and square root of n over 2, right. That is my sigma, and that is my mean, okay. Okay, and this is the Gaussian distributions, okay, that is for for n equals to 1000, and the histograms is basically I plot a histogram. So, here is this is also a PDFs, but yeah. So, I just assign to a hist variable here, histogram. Okay, all right. So, and the Gaussians, I basically create a PDF for the Gaussian distribution. So, this is basically normalized, okay, and this gives a normalized Gaussian distributions with a mean n over 2 and the standard deviations of square root of n over 2, okay, and where the x is basically n minus 2 times 4 sigma, mean minus 4 sigma to mean plus 4 sigma, okay. So, this is your sigma, right. So, this is my range, okay, and I plot this. Now, I mark this, okay, the hist and Gauss. So, you see, so this is again Gaussian. So, I start with the exponential distributions, but if the n is increases, okay, it becomes a Gaussian. So, initially I start with here I start with the binomials, okay, and this is also a Gaussians, right, at the end. Right. And in this case I start with the exponentials, okay. So, this is my exponential distribution, so, and I calculate, I draw the number from this distributions, from these exponential distributions, and then I calculate the basically the endpoints, okay, and make a table for these different samples, okay. So, I have a 10,000 samples. Okay. So, this is also a Gaussian. So, even though the worker only moves on the right, because my distributions are the exponentials and where the domains are only on the positive x axis. Okay. So, even though the worker only moves the right, a completely bias, okay, into one direction. So, there is a still spread in the final positions, right, that we already see, right. So, there is a spread and we calculate the spread, okay, that is the standard deviations, okay, because the length of the step is uncertain, okay, right. So, it is not always needed that we have to move both sides. Okay. So, there is a one side completely biased in terms of directions random walks, okay, but since the length of the steps is uncertain, right. So, in that case there is also spread in the final positions. Okay. And at the end we are basically get a Gaussian distributions, because this is a central limit theorem. So, the sum of n exponential variables will actually eventually looks like a Gaussians with a center n over 2 and with basically standard deviations of square root of n over 2. Okay. So, that is the central limit theorem. So, whatever your distribution start from, okay, if the n is increases, that actually lead to a Gaussian distribution. Okay. Okay, so that's all I discuss today, and this is the last tutorial sessions. Okay, so if you have any questions, please feel free to drop an email, okay, or put in the discussions forum. Okay, put your questions in the discussions forums. And those who opt for exam, okay, so I suggest you to go back to the lectures, okay, and also these tutorials videos that all these videos are available on YouTube. So go back and watch these videos, okay, and I also upload the files, PDF file and the Mathematica files, okay. So you just play with these files, okay, and the commands, okay, and if you stuck anywhere and go to the videos, okay, I explain in the detail. So I suggest you to go through these, okay, and yeah, and also the lectures that are uploaded in the NPTEL, okay, portal, okay. So I suggest you go through these and practice more and more, okay, and yeah, that's all, and all the best for your exams. So bye bye.